Today we are going to start a new chapter that is called atom, right? So before I start topic, I would like to do a brief introductions. So as we all know about atom, we studied about atom. Maybe you have studied quite detail about atom in chemistry also. All right. So first, what I'm going to do is in the introduction part, I would like to do a brief, historical study about atom, right? So the study about the study about atom was studied maybe 2000 years back. Maybe there are different philosophers in India, in Greeks, all right. So people try to understand what is the basic unit of and every matters, right? So the first scientific studies, right, about atom was studied by John Dalton, right? So the first model of atoms, all right. So maybe in Greek times, maybe in Indian philosophy, this all of philosophy, right? The atom related to philosophy, right? In a real sense, I mean, in a scientific, all right, in a science, study about atoms was first studied by John Dalton. So the first model of atom was given by John Dalton, right? So his study, right, his model was very similar to the model, the philosophical idea about atom by Greeks, right? So the term atom is derived from Greek atomo, right? That is the indivisible particle, right? So John Dalton, he was chemist. He tried to study the chemical combinations, right? So he put forward first model about atoms, and he said that atom is electrically neutral. Atom has no electrical charge, and and atom is the smallest. And he also says that every atoms, right, atoms of particular elements are identical, right? So atoms of different elements differs from one another, right? So that means every element has a unique atoms, right? So this is his idea, and this his idea. The aim is to explain the different combination, that is law of multiple proportions, and this all we have studied in chemistry, right? Definite proportion, all this, right? His few laws are there, right? So in order to explain those laws, those chemical law, he studied this model, right? And then in year 1897, the better model of atom was discovered, was done by J.J. Thomson, and his model is what we call as a plum pudding models, right? So James Dalton was responsible for the discovery of electrons. So he sees that electrons could come out from a metal, from an atom. So he said that electron, which is electrically negatively charged, is inside the atom. So as we all know, atom is electrical neutral. So he talked about the constitution of an atoms, composition of it. So he found that atom has electrically, basically atom is electrically neutral. So if he finds electron coming out from atoms, so the atom consists of positive charge as well as negative charge. All right. So regarding a plum pudding model, he says that atoms are like a watermelon, right? So electrons are embedded in atoms like the seeds of watermelon that we have studied in the lower class detail, right? So he talks about proton and electrons. He never knew about proton, but he said there exists a positive charge, right? The number of positive charge must be equal to number of negative charge, so that atom overall remain electrically neutral, right? Then the next the model of atom was studied by Rutherford. Rutherford was a former student of J.J. Thomson, right? So his model, right, is what we call as planetary models, right? So his model talks about, he talks about existence of a nucleus, right? This is what we call as Rutherford nuclear model of atoms, right? So he says that This we are going to study detail about this. He discovered a nucleus. There exists a heavy and mass which occupy a small space in an atoms, and electrons are revolving around nucleus. Right. This is his model. Right. And then just after a few years, Niels Bohr again studied in a Rutherford model, Rutherford laboratory, and then he just modified Rutherford model, and then his models we are going to study detail in this chapter. All right, is semi-quantum mechanics. All right, he could be able to explain much better than now. Schrödinger, these things are much higher, right, beyond our scopes. These things involves entirely quantum mechanics, so this could be able to explain much more than a Bohr model, right? So overall, these are the main, these are the different model of an atom, right? And this is the historical, the steps, all right, where how atoms develops, right? So model of atom has developed, right? So now what I'm going to do is first we would like to study Rutherford models, right? 1911, Rutherford put forward a new model of atom, and his model atom is what we call as nuclear model atoms. And his model of atom, his model of atom was the result of the experiment, right? This is what we call as alpha scattering experiments. So again, I have one more, Dalton 1803, then J. Thomson 1904, Rutherford 1911, and Bohr 1913. So these are the different model of an atom, right? Okay, now I would like to start a Rutherford nuclear model of atoms. So this model of atom was because of the result of experiment, right, carried out by two research scholar, Giger and Emerson, under the guidance of Rutherford, right. So these experiments consist of a source. This source is what we call as alpha particle source. That means alpha particle source means radioactive in nature, and alpha particles emit out from this alpha particle source. And then what we have is this is the experimental setup, right? So this is what we call the gold foils, a very thin gold foil of 10 raised to the power minus 7, and then if we allow alpha particle to pass through this gold foil, right? So we colliminate it, make a beam of alpha particles, and if we allow a beam of alpha particle to pass through these gold foils, and we would like to see the path of alpha particles. Alright, we would like to see the objective here is to see the path of alpha particles. We know alpha particle is positively charged, right? When I say alpha particle, it is a helium nucleus. This is equivalent to alpha particles, right? This is equivalent to alpha particles. Alright, so these things are done in a vacuums, right? So therefore no particle could hinder this experiment, right? And these are the screen. This is a zinc sulphide screen. When alpha particles strike the zinc sulphide screens, you could see a scintillation, you can see a shining things, right? So this is how we carry out, these two scientists carry out this. And now this is a much simpler experimental setups. So this is what I have, radioactive source, alright. This is the radioactive source is normally a bismuth, alright. So I would like to write down this, and this radioactive source give rise alpha particle of energy. This alpha particles of energy 5.5 mega electron volt is coming out from a source, and this source is what we call as bismuth, alright. Bismuth 214. And then the alpha particles come out, comes from bismuth source, and allow it to pass through a thin stick so that we get a beam of alpha particles. And this is a gold foils of a thickness 10 raised to the power minus 7 meter, a very thin gold foils. All right, and we would like to see the path of alpha particle, right? And this is the detector, right? This is what we call as detectors. This is what we call as zinc sulphide detectors. You put on microscopes, all right, then rotate this detector so that we would see where alpha particle, we could see the path of alpha particle, right? So I would like to write here, this is not there in textbooks, how alpha particles get out, how we get alpha particle out of bismuth. Bismuth is radioactive elements, right? And this undergo alpha beta decay, and we get the poloniums, and then we get alpha particles, and then we get lead. And this is how alpha particle, we get alpha particle out of this way. This is alpha particle, right? And this alpha particle having the energy 5.5 mega electron volt. This is alpha particle having this much energy. And then now I say the beam of alpha particle, when a beam of alpha particle falls on a thin gold foils, all right. So what we found experimentally, what we found is, this is strictly, the model of atom was came out from experiment only, right? So what we found is 1 in 8,000, all right, 1 in 8,000 atoms, alpha particles reflect, all right. That means out of 8,000, one alpha particle comes out, all other pass through it, so right. So when it is so most of alpha particle could pass through it without much deflections, and only few would come back, and that number is 1 in 8,000. So this shows that the gold foil or gold atom is a vacuum, or gold atom is empty, right? Gold atom is empty where you could pass through it. However, there exists a very a tiny a dense mass exists, all right, which could able to deflect alpha particles, right? So this experiment tells that there exists a heavy dense or heavy tiny mass which could able to deflect alpha particle even a 90 degree or more than 90 degree, or sometime 180 also. However, that mass is extremely very small. Why? Because the most of alpha particle could pass through it without much deflections. All right. So this is the experimental result, right? So when we just figure out this experiment in a graph, what we found is look at here. Look at here. So this is angle of scattering, right? Almost zero angle scattering is very high. All right. And look at here. This is 10 raised to the power 7, right? This 10 raised to the power 6. Okay. So almost like 180 deflection is very little, right? 180 deflection is very little, right? And look at here, as angle increases, number goes down, right? This is 10 raised to the power 2, that is 10 raised to the power 2 means 100. And this is 10 raised to the power 2, this is 10. All right. So that means, look at here, when you look at this, almost like 10 raised to the power, almost like 50 alpha particle in, how many are there? 10 raised to the power 7 alpha particles. 50 in 10 raised to the 7 alpha particles undergoing deflections or more than 160 degree, right? So that means this tells that alpha particles right, atom, right, gold atoms looks hollow, right, gold atom looks hollow, where alpha particle could pass through it, only few alpha particle undergoing deflection. So this is the graphical representation of Rutherford model, right? So however, and how do you know that the entire mass, right, the heavy mass present at the center, right? Why? Because when you allow alpha particle, a few alpha particle, maybe a 1 out of 8,000 undergoing so much deflections, undergoing more than 90-degree deflections, more than 110 degrees deflections. This tells that tiny nucleus is very, very heavy, right? So heavy that it could able to deflect alpha particle at such a high angle, right? So this is what we have. So now, after doing all these observations, what is the conclusion, right? Conclusion is nothing but the discovery of nucleus. So we say that now most of the alpha particle pass through gold foil without deflections, which means they do not suffer any collisions. So now we say that when alpha particle comes very, very close to a nucleus, there exists electrostatic force. There exists electrostatic force of repulsions, right? Alpha particle and a nucleus. Alpha particle and a nucleus. Alpha particle and nucleus. There exists what we call electrostatic force. Electrostatic force, and that force would be equal. We can easily measure K, alpha particle having 2e. This is gold, and this is the distance. R is the distance, right? Distance between alpha particle and gold nucleus, right? So this is what we. So because the deflections, right? And the deflection of alpha particle is all because of this force, electrostatic force. Deflection of alpha particle is all because of this force, right? Now, if a radius is very, if a distance between the two alpha particle and a nucleus is very close, then force is going to be much greater and the deflection is going to be much greater, right? So we say that most of alpha particle pass through the gold foil without deflections, which mean that they do not suffer any collisions, which mean that atom is hollow, all right, and only about 0.14% of alpha particles incident alpha particles suffer escaping of burst. So this is what we talk about. 0.14% of alpha particles undergoing a deflection more than 1 degree, all right. That means 99.86% of alpha particle undergoing a deflection less than 1 degree. That means that this shows the size of nucleus. The size of nucleus is extremely very small, right? A very small number of alpha particles, that is 1 in 8,000, suffer deflection more than 90 degrees. So this all talks about the size of nucleus and the mass of nucleus, right? Finally, we would like to conclude Rutherford models, all right, saying that electron would be at a distance of 10,000 to 100,000 times the size of the nucleus. All right, I'm sorry, this is nothing like that. Size of nucleus. All right, and that means, look at here, right? It is something like this, right? If I have atom of a size, let's say, radius 10,000 meter, right? Atom of a size 10,000 meter, right? And then size of a nucleus, size of atom is like that, right? So it means you can figure out that a size of a playground right? If I have a size of playground, if I have a size of playgrounds, and the size of a nucleus is something like one small tiny ball, right? This entire playground is atoms, and there exists a nucleus which is having the mass of entire playground, entire atoms, and which occupy a very small space. Small space is the which 1/10 O times smaller than times size of atoms. This is what we have. And then now next, the entire positive charge, most of mass of atoms are concentrated. That means most of atoms are concentrated. So therefore, this is the size of nucleus. This is the size of atom, and this is the size of nucleus. So size of atoms, or the size of nucleus is of 10 to the minus 15 to 10 to the minus 14. That means it is very small compared to atoms. Very small compared to atoms. The nucleus at the center is surrounded by a revolving electron in their respective stable orbits. Electron is bound to nucleus by a Coulomb force. That means this again says that the Rutherford model also says that electrons are bound to nucleus. Electrons are at a distance very far from nucleus compared to the size of nucleus, and still then they are bound to nucleus because of Coulomb force. So this is what we talk about atom, right? And then one more, right? We would like to do a small study about the trajectory path, right? So how Rutherford and his team could able to estimate the size of a nucleus, right? So here I would like to introduce one more concept called impact parameters. All right. So impact parameter is the perpendicular distance between the initial velocity of alpha particles, all right, and the center of nucleus. This is impact parameters. This is impact parameter for one. This is impact. These all are impact parameter, right? So these all are impact parameters, right? So impact parameter is the perpendicular distance of initial velocity vector of alpha particle from the center of nucleus. So that means if I send a beam of alpha particles, each alpha particle could have a different impact parameters, right? So now if an impact parameter, that is B, we found that if a B is very small, only then deflection is greatest. So now we would like to measure the B for alpha particle, B of alpha particles which undergo deflection more than 90 degrees. So that means we would like to find out B for alpha particle whose deflection is more than 90%, right? So we found that the B is extremely small. The size of B range from 15 meter. That means this could be a size of nucleus. If a B is very large, then deflection is almost zero. So this is what we talk about, alpha particle trajectories, right? So the entire model is based on alpha particle trajectory of alpha particle, right? So why there is a deflection? Deflection is because of electrostatic force of repulsion between alpha particle and a nucleus. So it was very well confirmed that nucleus is electrically positive. Why? Because there is a repulsion between alpha particle and a nucleus. And then now his model could talk about orbit of atoms, right? So orbit of electrons. So when we talk about so we say that this is nucleus and electrons are revolving around nucleus. Electrons are revolving around nucleus. All right, electrons are revolving around nucleus. So when electrons are revolving around nucleus, there must be a centripetal force. There must be a centripetal force, and centripetal force is provided by, when the electrons are revolving around nucleus, there must be a centripetal force, and that centripetal force is provided by electrostatic force. So therefore, I just write here, this centripetal force is called electrostatic force. All right, and what is that centripetal force? mv square by r equal to, what is electrostatic force? This is equal to for hydrogen atoms, we say this is equal to 1 by 4 pi epsilon naught E square divided by R square. This is for hydrogen atoms. Why hydrogen atom has only one electrons, right? So therefore, now we would like to write this. This is what? Since the centripetal force is provided by an electrostatic force, this goes around nucleus like this. So the whole idea here is that electron is going around nucleus, and how electron could go around nucleus is all because of electrostatic force, right? This is the charge. All right. Now these electrons going around nucleus has potential energy as well as kinetic energy, right? What about potential? Potential energy would be equal to potential energy of an electron would be equal to E square divided by 4 pi epsilon naught r, where r is a radius, where this r is a radius. This r refers to a radius. This r refers to a radius of an atoms. This r refers to a radius of an atoms. And now look at here. I'll simplify this. If I simplify this, this is equal to, r is equal to 1 by 4 pi epsilon naught E square divided by mv square. This is one way. Again I can write this. This is mv is equal to, mv square is equal to E square divided by 4 pi epsilon naught r. This is mv. Now this is potential energy is given by E square divided by 4 pi epsilon naught r. Now what about kinetic energy, right? So kinetic energy of electron is given by half mv square. All right. What is mv square? Mv square is equal to, mv square is equal to 1 by 4 pi epsilon naught E square divided by r, where r is the radius of an atom, right? So therefore this is equal to 1 by 8 pi epsilon naught E square divided by r. This is now look at here. I would like to write here minus. I'm sorry, right? I missed the minus. Why minus? Attractions. Potential is attraction. Whenever potential is attractions, potential energy is negative, right? If repulsion, potential energy is positives. Now what about the total energy of an atom, right? Total energy of an atom, right? So total energy is equal to kinetic energy plus I write here kinetic energy plus potential energy. So what is kinetic energy? 1 by 8 pi epsilon naught E square by r. What about potential energy? E square by 4 pi epsilon naught r. And finally we got this is equal to minus E square divided by 8 pi epsilon naught r. So this is the total energy of atoms. Now look at here. When you look at these equations, the total energy is negative, which implies that electrons are bound to nucleus. So negative sign implies that electrons are bound to nucleus. Electrons are bound to nucleus because of electrostatic force of attraction between electron and a nucleus. All right. So this is the total energy of an atom. This is so negative total. The negative sign implies that electrons are bound to nucleus. Why electrons are bound to nucleus? Because of electrostatic force of attraction between electron and atoms, right? So now electron and a nucleus. Now here in this model, what we are talking about is we are talking only one force, that is electrostatic force, the Coulomb force between nucleus and atoms, nucleus and electrons. Electron is electrically negative and the proton is nucleus is electrically positive, and because of which there exists a force and electrons are going around nucleus. And this is very classical. This is a classical model of an atoms. All right. So this is what we have now. So this is what we have. So with this, I'll come to conclude this topic, and then next I will talk about a Bohr model of atoms. Before I start a Bohr model of an atoms, we would like to talk about spectral lines. Thank you.